last time, and so we'll go to chapter 15. Why not? So in chapter 15, we're going to talk about solutions. We're going to talk about solubility. We'll also talk about how to calculate things like concentrations for solutions. And we'll also talk about, towards the end of this chapter as well, stoichiometry that involves solutions. So let us get into it here. So first off, an aqueous solution, many important chemical reactions and a lot of biological type reactions do occur in sort of an aqueous environment. And when we talk about an aqueous environment, those are really the guys that we've seen in sort of reactions that have obviously the AQ symbol sort of next to it. And just a reminder that if something is aqueous and something that is a solution, is different than something that has the L sort of symbol next to it or a liquid. Something that is a liquid is a pure liquid, which means it's really just in there with it. So again, if you had just water by itself, that would be liquid. If you took something like water, as we might have talked about, and you add some, say, sodium chloride to it, the sodium chloride would dissolve in the water and it would make a sodium chloride solution that would get the aqueous symbol. So again, that is the difference between, something that has the L symbol and something that has the aqueous symbol. Now, when we talk about a solution is a homogeneous mixture of two or more substances. And if you remember, homogeneous means that pretty much everything mixes. Everything is the same throughout. So that's basically what a solution is. There really is two parts to a solution. The smaller part of the solution is known as the solute. And that is usually the thing that is sort of dissolved in the larger part of the solution, which is known as solvent. So both of those things together, the solute plus the solvent, basically will get you a solution. So in my example up here with the water and the sodium chloride, it is the sodium chloride that would be the solute, and water here would be the solvent. We'll talk about it, but water is a very good solvent for a lot of things, not so good for other things, but it's used a lot as a solvent. But water doesn't always have to be the solvent that's used. And again, in certain cases, you would not want to use water as your solvent because it wouldn't work very well. The easy way to always identify if you have a solution, sort of what the solute is the name of the solution. So if you have a sodium chloride solution, the solute sodium chloride, if I spit that out. If you have like a, potassium nitrate solution, potassium nitrate's the solute. So really the name of the solution is always going to be the solute. So that's sort of an easy way to determine what it would be. Now, water, as I mentioned, is a very effective solvent for a lot of things, but again, is not good for everything. But water, for many reasons, including the fact that it is polar, which is the main reason here. If you remember, water, again, is a polar molecule. So it is the oxygen side of water that is more negative, and it's really the hydrogen side that's more positive. And that, again, is a result of really unequal sharing of electrons over the entire molecule, like we talked about in bonding. And that works really well for things that are polar, that also have, obviously, a positive side and a negative side. They're able to do those intermolecular forces that we talked about the other day. They can do some dipole-dipole interaction, some hydrogen bonding, perhaps interaction. It's also really good for a lot of ionic compounds, because when a lot of ionic compounds go into water for a swim, they essentially will break apart into ions. And because water has both a positive side and a negative side, it allows water to basically surround each of these ions when they go for a swim. So the positive guy is surrounded by the negatively charged side of water, which is the oxygen side, while the negative ion gets basically surrounded by the positive side of water, which is the hydrogen side. That really does two things. It allows actually something like sodium chloride, which is ionic solid, to actually dissolve. So because there's just so much water in there, obviously, there's a lot of water molecules. They're able to actually kind of pull apart the ions from each other when they go for a swim, and they will actually keep them separated from one another. Obviously, if the water molecules were to disappear, the ions would come back together and that solid would be reformed. So because they have very similar type of interactions, what's actually happening here in this interaction is something we also talked about, I think, the other day. This is what is sometimes referred to as ion dipole interaction. Ion from obviously the ions, and dipole from the polar molecule like water is basically the interaction that's occurring when you put something like sodium chloride in water and it dissolves. Any questions on that there? This process is, again, what is referred to as sometimes hydration, basically hydrating a ionic solid with water. And like I mentioned, it does almost provide like a buffering between these two guys. As we also talked about, I think on Monday as well, the attraction between the positive ion and the negative ion is a very strong one. That's an intramolecular force. As we talked about, that's pretty much your strongest type force that you could have. So the waters are able to really kind of keep them separated from each other, because without the water there, they definitely would want to come back and stick together again. And that is, again, what we see if we were to take a wonderfully drawn Bunsen burner there, also known as an arrow, and we were to heat this solution here. Basically, we would obviously start to evaporate off all these waters, right? And at that point, there would be really nothing in the way of the positive ion and negative ion from coming back. And again, as we might have talked about before, that's like the earlier experiments that we did in this class, where you took the salt water, you kind of evaporated off the water, and you're able to see sort of the solid salt residue basically come back together as a result of basically removing the water from between those ions. We also could help something like, say, a salt or sodium chloride dissolve, because typically when we do put it in water, we do a couple of things, like we usually will stir, right? So as we stir, we're also providing energy to that system. And in addition, we're also throwing a ton of water all over all those ions, right? And allowing them to basically start kind of plucking off each of those ions from the solid. And that's what we see here. Again, in solution, water molecules, which are these guys, are going to come, and they're basically just going to kind of pluck off these ions, helped out by the stirring and the extra energy, and really throwing the water everywhere. And again, going to basically hydrate these ions as they kind of go off and start to dissolve. And in terms of, types of bonds that we've talked about, obviously in previous chapters, it's important in terms of sort of the interaction that you typically will see when you do something with water, or in terms of solubility of a salt or something like that. Just a reminder, obviously, hopefully we remember, but ionic bonds, right, are always between metals and non-metals. And again, that's caused by really a redox sort of situation where we are losing electrons and gaining electrons that occur. And that's different than what we see in a covalent bond, where we have basically two nonmetals that are sharing electrons. And whether or not in a covalent situation we end up with sort of a polar bond or not, right, is dependent on really the electronegativity and how those electrons are going to be shared in a particular bond. And that's really important, especially when you're dealing with sort of molecular compounds or covalent compounds, is you may have, a molecule, for example, that, some of it is really non-polar. So you look at something like this, which is methanol. Those are all carbons and hydrogens on that side, and that's really non-polar. But it does contain this one little bond over here, which is an OH bond. And again, based on electronegativity difference, that actually would be a polar bond. And the oxygen here would again be more negative. The hydrogen would be more positive on that part of that molecule. And that's enough for something like that particular molecule to actually be soluble in water, because it has that little part of it that's able to interact well with something like water, and it would actually be fairly soluble in water. So, even though we think maybe about things sort of sharing electrons, Maybe, you know, we don't have ions or things with charges, but, you know, there are certain parts of these molecules that, you know, can have a polar part to it, even though it may have like a non-polar part as well, that can allow it to interact well with things like water, and obviously would increase the solubility of it. Obviously, if something is soluble, right, that basically means that they sort of mix, right? And if something is sort of insoluble, you know, they really don't mix well with each other. So in the case of a polar covalent bond, again, that electronegativity really helps us find the place on certain molecules that can interact with each other. And obviously, we've talked about polarity of bonds and bonding. So let's talk about some examples of things that are soluble in water. So for sure, anything that is ionic, which will break apart into ions, will really be soluble in water. And again, it's going to really be like what we just talked about there, sort of that ion dipole interaction that's going to sort of occur. You're going to have the water, which is polar. You're going to have these guys that are going to break apart into the positive and negative ions, and they pretty much are going to be soluble in pretty much all cases. But again, as I just mentioned a second ago, there are things that are really not ionic compounds, more covalent compounds that are also soluble in water. So things like sugar, which is basically a bunch of nonmetals together, carbon, hydrogen, and oxygen. And obviously that's going to be held together by sharing of electrons. And something like ethanol, which is this guy right here, kind of looks like the last one I drew with an extra carbon in there. So this is ethanol up here, and this is obviously the basis of sugar. And really what they both really have in common is kind of what we were just talking about. They have this OH group. So something like ethanol here has the one OH group, and that is really the spot where it can interact with water. And if you had a water molecule there, again, the oxygen is negative, the hydrogen is positive. This is where they're able to basically interact with each other through these guys. This bond between the hydrogen and the oxygen is known as what we talked about on Monday, hydrogen bonding. So that is hydrogen bonding that's occurring, which is a relatively strong intermolecular force that we talked about. And that makes it, you know, really soluble in water. The deal with sugar is, as we'll see a picture of it in just a second, but pretty much sugar is pretty much littered with OH groups kind of all over it. So it has a lot of OH groups on sugar, and that makes it really soluble in water. Pretty much anywhere there's sort of an OH group on that guy, it gives it a place to interact well with water, and it makes it really, really soluble. Even though sugar is a much larger compound than, say, something like ethanol, it has a lot more sort of OHs to basically compensate for that. So here's sort of a picture of that process here. Here's methanol in our water, again, able to hydrogen bond between them two. And again, that's a pretty strong sort of interaction that occurs. Obviously, here's our ethanol doing the same thing, hydrogen bonding. A reminder that not all things that have hydrogen can hydrogen bond. As we talked about on Monday, for hydrogen bonding to basically occur, you need basically a hydrogen that is bound directly to either nitrogen, oxygen, or fluorine. So that is why this hydrogen here could hydrogen bond. It is directly bound actually to the oxygen, and that's really what you need to look at. And same thing in water, really. This is the oxygen that is bound directly to that hydrogen, allowing it to hydrogen bond. Again, really the reason for that, as we talked about, is those are pretty much your three big electronegative elements there, as fluorine is the most electronegative. So it creates a really big sort of separation of charge on the bond between, say, oxygen and hydrogen, and that allows it to interact really well and do this sort of hydrogen bonding that occurs. Any questions on that there? Now, Does the solubility of something like this decrease as you build out perhaps more of the non-polar side? And the answer is yes. So, we have something like ethanol, which has really, kind of this part that's non-polar. If we had something that had a lot of carbons and hydrogens, basically, and then it maybe had the OH group at the end. And again, all these other guys here are hydrogens. You get the idea, hydrogens all the way to the end there. Now, something like this, if we wanted to sort of see if it's going to be soluble in water, it is probably not going to be very, very soluble in water. And that's because what we pretty much have is a ginormous part of the molecule that's nonpolar. And we have just this little part over here that can interact with water. And it really does decrease the solubility a lot, to the point where it's not very soluble at all. It's sometimes referred to, that's an organic type molecule, sometimes referred to as was referred to as steric hindrance, which basically means that big part gets in the way of the OH being able to basically interact well with water. So typically, if you have something like these guys, which are really more organic molecules, once you get to about 4 or 5 carbons, that's sort of the max. You hit 6 or more carbons kind of built up onto that OH group, the solubility drops tremendously to almost not being soluble at all, because it's just too big for it to interact. So what about oil and water? They obviously do not mix. Oil is insoluble in water is probably the better way of saying that. Oil is insoluble in water. And that is because oil is pretty much what I just drew without the OH group. It's pretty much just nothing but a long chain of carbons, like octane, like you fill up in your car, like 8 of them in a row, and hydrogens basically. And obviously the carbon hydrogen electronegativity difference is 0.4, as we talked about in bonding, and that is basically your non-polar type of thing. Because they are usually very, very long and they're non-polar, as we talked about the other day, something like oil, which is non-polar, is going to mainly use a specific type of intermolecular force, and that was those dispersion forces. So something like oil will use dispersion forces, which you remember are these like temporary weak type of interactions. And if you try to put that into water, which is going to mainly try to use hydrogen bonding, that is a bad mix. Those are two very different sort of ways to interact with each other. Can they interact for a short period of time? They can, because everything could do some type of dispersion force. But over the long period of time, they will not be able to maintain that. And as we talked about, like the oil and vinegar sort of salad dressing, right? You can mix it and it will mix, but eventually it will kind of separate out. And that's what will happen. Oil will end up floating on the water, right? Like an oil spill, right? Oil floats on the top of the water. And that is, again, because they don't have no long way to interact really well with each other. The other important thing about that is when you actually try to dissolve something in water, what you're essentially doing is replacing sort of the water-water interaction with each other, and you need to replace it with something that's very similar. Water is a relatively small molecule, so when you try to drop oil in there, it doesn't really fit very well. It's kind of like, you could park the semi-truck in the garage, but you probably won't get it all in the garage, right? Some of it will be hanging out and stuff like that. So, maybe it works, but it doesn't really work really well. And that's sort of the same idea. So when we talk about solubility, there's a phrase you oftentimes hear, and that is the idea of like dissolves like. And what that means is things that have very similar intermolecular forces will be very soluble in each other. So things that basically interact the same way with somebody else as they do with themselves will be very soluble. And things that basically are using really two opposite types of intermolecular forces will not be soluble in each other. What that basically means is, if you have something that is polar and polar, that's good. They are going to be soluble in each other. If you have something that's ionic, and polar, they are going to be soluble in each other. Again, they could do that ion dipole interaction. And if you have something that is nonpolar and nonpolar, they will also be soluble in each other because they both are using dispersion forces, so they can mix really well. You really only run into a major problem when you try to cross over there, and you get things that are going to be insoluble in each other when you try to put a polar guy and a non-polar guy together, or even an ionic guy and a non-polar guy together. They're not going to be able to interact really well. So polar and polar things should be soluble. Ionic polar, non-polar, and non-polar, which is the one people sort of miss on. So non-polar and non-polar are soluble in each other. But again, that kind of crossover to polar and non-polar are going to be insoluble, or even again, ionic and non-polar should probably be insoluble as well. Any questions on that? Yeah. Yeah, so I mean, in terms of, you could add some things that can change sort of the solubility, and they would have some properties that maybe are attracted to both things. So it would allow everybody to sort of mix together. But just what we're talking about here is just generally just kind of putting two things together without any sort of things added to increase the solubility. But that would be, sort of what would be happening in that case. They would be able to kind of interact with both things, and kind of almost like a bridge, right? To allow those things to sort of, everybody to sort of mix and stuff like that.
So would it actually be changing the properties of the two things that it's trying to mix, or is it the thing?
It's the thing that's able to sort of interact with both things. So maybe this is not a best example, but for example, like something like soap, right? Soap has like a non-polar side and a polar side. And the way soap sort of works is it's able to, because it has a non-polar side, it's able to grab up all the dirt. And when it grabs up all the dirt, because mostly dirt is non-polar, so it's able to interact really well with that. And what it does is sort of arranges itself in a way where it kind of makes all the dirt go kind of interior with the non-polar part of soap, and the outer part of soap, for example. So like all the non-polar guys here kind of get mixed up in the middle. I'll just draw lines as the non-polar part of soap. And the polar part of soap, which I'll just represent with the little charge at the end there, finds itself on the outside. And what you typically do after you soap up, right, is you wash it off with water, which is polar. And that part of soap is attracted to the water to come through. And because it's sort of grabbed onto all the dirt that's in the middle, the dirt and everything goes out with it. So it's more probably, that whatever is added to it has some attraction to both. And it's possible to have something like that where, there's kind of like a non-polar side and a polar side that can arrange itself in a way that will help bridge it. Other questions? So here's a couple of pictures. Here is sugar. And like I said, although it's a relatively large molecule, it pretty much has a lot of OH groups, again, all over it. And everywhere there is pretty much an OH group, again, it gives it an opportunity to interact through hydrogen bonding with water and makes it really, really soluble. Down on the bottom is pretty much oil. And it's just a long chain of carbons and hydrogen, which is non-polar. And as we talked about, basically non-polar, very large, going to be using dispersion forces, not going to be able to interact with water really well. And this is typically what we do see sort of happen between oil and water. And again, all these water molecules are hydrogen bonding. These guys are dispersion forces. And like I said, there is going to be, some mixing that will happen, but there's no way for it to maintain it. So over time, we're just going to get that sort of separation that occurs. And this is typically what you find when you take something like oil, which is kind of organic, and something that's sort of aqueous or water-based. This is usually the separation that you see, even in a test tube. The more organic guy ends up on the top. They've kind of water layer and stuff. It usually ends up on the bottom of the test tube. Now, when we talk about solubility, one when we do have one substance like a solute that will dissolve in another, that is basically what is known as being soluble. So if we have a solid and you put it in something like water, we would expect it to dissolve. We could even talk about liquids being soluble in each other. Obviously, if you take two liquids and mix them together and they're soluble in each other, what you will see is basically just one layer looking, right? So all those liquids will mix together. You won't see any type of layering that will occur. When we take one substance that doesn't dissolve in another, it's said to be insoluble. As we just saw there, oil is insoluble in water. And again, if it's a solid, it won't dissolve, obviously. And if it's two liquids, what you would see is some layering that would happen of the different liquids, like we saw in that last slide there, where the oil layer is on top and sort of the water layer there is on the bottom. Sometimes people talk about liquids and solubility as being miscible. So if something is soluble in sort of a liquid fashion, sometimes they say they're miscible with each other. And if they're insoluble, they're immiscible with each other. It's a couple of terminologies sometimes used. Now, there is usually a limit to the solubility of one substance and another, and it is based on temperature. So for example, you know, if you take some sugar packets and you pour it in some water and you mix it, it's going to dissolve. If you take the Costco size thing of sugar and pour it into obviously a beaker of water or a small cup of water, at some point, it's not going to dissolve. You're going to hit a limit to how much can dissolve. And oftentimes it's temperature based. So usually a solid in a liquid, if you increase the temperature, you can sort of increase the solubility, allow a lot more of the solid to dissolve, and vice versa. Obviously, if you kind of lower the temperature, you'll have a little bit less that will be able to dissolve. Gases are always soluble in one another, and that's pretty much because gases are doing nothing but flying around. So just by that process, they are flying around. And if you have several gases, they are constantly mixing with one another. So they are soluble, obviously, with one another. Some liquids are also mutually soluble with each other. So that would be like your polar and polar guy, or your non-polar and non-polar guys being soluble in each other. Again, only usually run into a problem if you kind of cross over and try to mix those non-polar with polar. Now, as we talked about with like dissolves like, some other things that sort of affect solubility. At higher temperatures, we typically, like I said, do see a larger solubility of a solid in a liquid. And that's because if you increase the temperature, you're increasing the energy. And if you think about it, if you have something that's a solid, it's a bunch of ions kind of stuck together. And if you increase the temperature, that is going to do two things. It's going to obviously supply some extra energy to that solid. It's going to give those guys a little bit more vibration, if you will, and allowing them to maybe come off a little bit easier. It's also going to probably help move the water molecules around a little bit faster as they're also getting some energy. And it's going to allow them to interact really, really well. The opposite, like I said, is true. If you kind of lower the temperature, you know, those guys in the solid are going to have a little bit less energy, not going to be moving around as much. So they're going to kind of stick there a little bit longer, and you would start to see a decrease in the solubility. When we have a lower temperature, we have a larger solubility of a gas in a liquid. And that is because if you have a gas that's going through a liquid and it's at a lower temperature, it's going to be moving slower, which means it's going to stay in the liquid part a lot longer than if you had a gas molecule at a higher temperature. It's just going to zoom around really fast and be able to sort of escape the liquid part really a lot faster. Solubility of gases also depend on pressure. And as we talked about with like Boyle's law, pressure and volume are related to each other. So typically when you have a higher pressure, do we have a large volume or a small volume? So at a higher pressure, we typically have a small volume, right? They go opposites of each other in terms of Boyle's law. And so when we have a smaller volume, that means that those gas molecules are going to be pretty much shoved down into the liquid part. That is what we like to call Henry's law, also the soda pop type thing, right? Before you pop the can, right, all the CO2 is dissolved in the liquid part. And that's because it's under a lot of pressure. probably about 4 times atmospheric pressure it's under, and it pushes all those gas molecules, the CO2, to stay in the actual liquid part of your beverage, which is why when you pop it open, you do 2 things. You release the pressure and also give it an escape route, which is all the fizzing you see come out, right? It's all the CO2 is now going to escape the actual soda and stuff like that. And that's also why when you leave your soda open up for a while, you come back and drink it, it tastes very flat, right? Because you released all that pressure and gave the gas an escape route out of it. And that's why your soda feels very flat, right? That's why it doesn't feel as flat when you have a screw cap, right? Type of guy, because you put this cap back on, prevents the CO2 from completely escaping. Takes a little longer for it to go flatter in those type of situations. That's what's actually known as Henry's law. There's actually a relationship that you could calculate the pressure of a gas in a liquid type of thing. When you get to 1A, you'll probably do that, I think, usually. So let's talk a little bit about solution composition. There's a couple of different ways that we do classify a solution. Let's just zoom in case you missed it there. So what happens if we have a situation where we added too much solute to the solvent? We get what is known as a saturated solution. A saturated solution is pretty much a solution that has hit the point where no more solid will dissolve. So you pretty much at that particular temperature got as much solid in that solvent that you could get to dissolve. What that means is, again, if you're at that point and you continue to add solid to it, it will not dissolve. It'll just start piling up there on the bottom of the beaker or the test tube. Now, the opposite of that is what's known as an unsaturated solution. And an unsaturated solution is pretty much a solution where you have not got there yet. So you have not hit what is sometimes referred to as the saturation point, which is what happens at a saturated solution. So it will actually continue to dissolve solid if you put more in. It will continue to dissolve the solid until you hit a saturated solution. And then at that point, it will no longer obviously be able to dissolve any more solid. Again, it is really temperature dependent, as I talked about. So, you kind of increase the amount of solid by increasing the temperature. So saturated, no more solid will dissolve. You're at the maximum amount that you could get in there into the solvent. And unsaturated, you're not there yet. You could still continue to dissolve at that point. So if you were doing this like in a test tube, you scoop some solid, you kind of stirred it, it dissolved, you scoop some more solid, it's dissolved, you're still an unsaturated solution till the point where you scoop some solid in there and try to get it to dissolve and it no longer dissolves, then you most likely have made a saturated solution at that point. Any questions on that there? Yeah.
And this is going to apply across the board as far as definitions, like if you're combining 2 things and it completely makes a new product. When you're talking about A and B, and when you combine them to make C, you're saying that it's miscible.
Yeah. So what we're really talking about here is not necessarily making a chemical reaction, if you will, in a sense. What we're talking about here is like really making a solution. So there's 2 parts to the solution, which is the solute, which is the smaller part, and the solvent, which is the larger part. So, if you were to make something like, say, a sodium chloride solution, you would grab some solid sodium chloride, which would be your solute. You would grab some water, which is a liquid, which would be your solvent, and you would proceed to basically put the solid into the water. Is it really a true chemical reaction? And not really, because it's kind of a physical sort of change that's happening. But we would put that in there, we would mix it, and the sodium chloride would dissolve, and you keep doing it. But then you got tired and you dumped the whole bucket of sodium chloride in there and you started to mix it. At that point, obviously it won't dissolve, and you're definitely hit a saturated solution, probably went past it. But at some point, if you continue to sort of put the solid in there to the water to dissolve, at some point it will stop dissolving, and that would be basically the saturated solution at that point.
That would also apply if your intention is to have a chemical reaction in the process.
Yeah.
That's how you'll say. That's how you would describe it.
I don't know if in this process of making a solution would necessarily sort of be a chemical reaction, maybe like you're thinking. It's again more of a physical change because, you know, if we took that at the point when we stop, wherever we stop with putting the sodium chloride in, you basically have just one thing. You have just a sodium chloride solution. You don't really have anything else there. So it's really more like a physical type of change that's sort of occurring when you're making that solution. And we know it's physical because we can simply just take that sodium chloride solution that you made, heat it, all the water would evaporate off and we'd have our solid back. So it's more of a physical change than a sort of a chemical. Yeah. Yeah. And that's basically what a solution is, which is a homogeneous mixture, which is, you know, as we talked about with mixtures, those are really physical type of changes that occur because they retain their own identity. So there's really no chemical reaction occurring. So remember, a chemical reaction is a chemical change, which means what you start with and what you end with are two fundamentally different things. And yeah,
that was my point. So
yeah.
I understand the physical part of it and
Mhm.
where we have to live, but I think and I might just be going the wrong direction. When you're in the process, even when you're trying to mix whatever, with the intent to observe a chemical change,
Mhm.
or you know it's gonna result in a chemical change when you're mixing.
There won't be really any chemical change that would happen in this
Okay,
process.
okay.
There won't be. Yeah. Now, if you took that sodium chloride solution, then added some other like chemical to it, then you perhaps could have a chemical reaction. Right? So for example, you took the sodium chloride solution, you added silver nitrate to it. When those two guys would come together, then you would have a chemical reaction that would occur. It wouldn't be because it would actually make they wouldn't be miscible in a sense because there would be something there that would make a solid. It would make like silver chloride based on solubility rules. So there's parts of it that would be kind of mixing with each other, and there's parts that wouldn't because of the silver and the chloride would come together and make a solid. Yep. Okay, you're welcome. Other questions? Now, there's actually a third way you could classify a reaction. I think we'll see it maybe today, and that is what is known as a supersaturated solution. A supersaturated solution is like a saturated solution, but super. And thank you for not laughing. All right. So how do you typically make a supersaturated solution? Well, typically you start actually with kind of making a saturated solution. So you typically make like a saturated solution. And a lot of times when you're doing this, you're actually going to kind of heat it up a little bit. And when we heat it up a little bit, what that's going to do is increase the solubility of whatever we're dissolving in it. And by heating it up, it's going to way increase the solubility. And that's pretty much going to allow us to get a lot of that solid in here to dissolve. And typically when you make a supersaturated solution, after you kind of heat it up, you get a bunch of stuff in there to dissolve. What you typically do is just let it cool down. And you pretty much don't touch it. And what happens now, I heated it up, I got a lot of stuff dissolved in it, right? When it cools down, what happens to the solubility? It should also come back down. But it's a little late at this point because we already dissolved all that stuff in it when we were heating it. So as it cools back down and you don't disturb it, what you're going to end up with is really a supersaturated solution. And basically a couple of things happen there. As I said, by heating it, we're able to get a lot more solid dissolved. But in the process of heating, we're also going to be evaporating off some of the water that was there, right? Just through that process. So what we end up with at the end is a solution that has way too much solid dissolved in it. Actually, probably has a little less solvent than it started with, water. And now we get a very like unstable solution here. A lot of them are very unstable. It is so unstable that if you just took like a speck, like that big of a speck of whatever you dissolved in it, and you just took it and dropped it in, that is enough for it to go, whoa, that's like too much dissolved. And what it will do is it'll actually go from a liquid, and we'll say that, you'll hear it later, it will say that exact same thing right there. When you drop that little guy in there, all the solid that's dissolved will decide, no, thank you. and it will come out of solution, and it will go from a liquid sort of state to like a rock hard solid state, because it knows it's got way too much dissolved in there. And that little guy is enough to just push it over the limit, and all the solid will basically come out of solution. It's a fun experiment. I think we'll demo it later today. It's also sometimes so stable that, even before you get to the point where you drop the little guy in there, you actually touch it too hard or put it down too hard. That's enough to cause it just to come out of solution and start that whole process. It's so unstable like that. Years ago, they used to let you guys do it, or at schools let students do it. But what they'd have them do is like do it in a test tube, heat it up, have a thermometer in there, and then they would do the part where they add one drop, and then they had like a test tube stuck on a thermometer, and the kids would go, how do I get it out? And I would recommend that move, but that's not the right move. So they don't let people do it that much. They lost a lot of test tubes and thermometers over the years. All right, any questions on that? Wonderful things. All right. There are a couple other ways we could describe solutions. Is concentrated. A concentrated solution has a relatively large amount of solute that's dissolved in there, and a dilute solution has a much smaller amount of solute that's dissolved in there. As we'll talk about, one of the most common units of concentration is molarity, which is big M. And if you ever looked at any of the bottles that we use, there's usually a number in front of the big M. And the larger the number, the more concentrated it is. The smaller the number, the less concentrated it is. This is like your idea of, like you grab the big gulp before class, right? Tastes really good. Got a lot of ice in there. You go to class, you come back to your car, all the ice is melted, right? And basically it's now become a lot more dilute. You drink it because you're thirsty, going, how bad could it be? Then maybe you regret it after you do that, I suppose. Yeah, but obviously it doesn't taste as fresh from the fountain, if you will, after all the ice has melted. And in that process, basically what you did is you add solvent, right, from the water coming from the ice to the syrup and everything else that may be in your beverage. All right, now that we talked about different ways for solutions, let's talk about some concentration units involving solutions. The first one is what is known as mass percent. And mass percent is sometimes abbreviated as percent M/M. So that's mass to mass percent is what that refers to. To calculate the mass percent, we take the mass of the solute divided by the mass of the solution times 100%. The important part of this calculation is actually the bottom part. Very common in these type of problems that involve mass to mass percent. They will give you the mass of the solute and the mass of the solvent separate in the problem. So it's very common people will mess up by just taking the mass of the solvent, but you do have to actually add those numbers together in a lot of cases, especially in these problems. There's very common, they kind of separate it out. So again, that's what this says down here. The grams of the solute plus the grams of the solvent will give you really the mass of the solution there. And again, you want to make sure that you get both of those guys. Otherwise, if you just do the solvent, obviously you will get the incorrect answer. You could also use, if it said something like you had a 5.2% by mass sodium chloride solution, you could actually take that and kind of turn it into a conversion factor to use in a problem. Because this is basically grams over grams, that basically means that you would have, in that case, 5.2 grams of sodium chloride and 100 grams of solution. Or because it's like a conversion factor, you can use it the opposite way around. 100 grams of solution will give you 5.2 grams of sodium chloride. So, if you're given the percent by mass, you could do two things in these calculations. You could just plug and chug into the actual formula here and it will come out right. Or you can sort of do the calculation more like a dimensional analysis problem, sort of like conversion factors, and just cancel out the units. And that's another way that you could kind of do these problems. Obviously, we just assume 100 grams because that keeps the numbers the same. You could assume whatever or many grams as you want, numbers would change, but it's just easier, obviously, to assume 100. Any questions on that there? All right, let's try one here. A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. Calculate the mass to mass percent of calcium chloride. So to commit, see what you come up, but we're looking at mass to mass here. And that is the mass of the solute divided by the mass of the solution times 100%. Here, the calcium chloride is a smaller number than the water, and that is going to be our solute here. The water here is going to be our solvent, as it's the larger part. So we're going to put those guys together to make the solution. And since it's a calcium chloride solution, that's how you know also that the calcium chloride is a solute. That means that the mass of the solute is the 2.5 grams. The bottom part, though, is not 50, but we do need to add both of those together. So it is the solute, which is 2.5 plus the 50 grams to get us the total mass of the solution, which would be 52.5 times 10 or 100. Would be better. And if we do that, 2.5 divided by 52.5 times it by 100 gives us a 4.76% by mass calcium chloride solution. Any questions on that calculation there? What does that basically mean? It basically means for every 100 grams of solution, you got about 4.7 grams of calcium chloride that has been dissolved in it. Yeah. Any questions on that one? All right, let's try another one here. Try the next one that you have. Which should be this one, I think. Concentrated hydrochloric acid solution contains 37.2% by mass. Hydrochloric acid, what is the mass of the HCl that's contained in 35.5 grams of the concentrated hydrochloric acid? Give a hint there, solution. Okay, so again, we're obviously dealing in percent mass to mass. So you can use the formula here, the mass of the solute divided by the mass of the solution times 100%. Here we are given obviously the percent mass to mass, which is 37.2%. We're also given the mass of the solution, which is 35.5 grams. And we are looking for the mass of the solute. Now, how did I know if I didn't write that that was the solution? It's because they asked me to find the mass of the HCl. And again, pretty much the name of the solution is the solute. So that is how you know that is what you're trying to find, and that the other guy would be the mass of the solution in that particular case. So you could definitely plug and chug into this equation, or again, you could do more of a dimensional analysis approach. They both should give you the same answer. So I'm just going to do the dimensional analysis approach so that you can, again, kind of see it that way. 37.2% means I have 37.2 grams of HCl and 100 grams of solution. Or again, you could do 100 grams of solution over 37.2 grams of HCl. So since I do know the mass of the solution, I could take the 35.5 grams of the solution. I could use the conversion factor here on the right or the left, your left. That would be 37.2 grams of HCl over 100 grams of solution. Grams of solution will cancel, I believe 13.2 grams of HCl is what you should end up with there. So you can take, again, a more dimensional analysis approach to it. Is it any different than plugging it into the equation? It is not. It's the same math. Basically, you are basically have this number. So you're going to divide by 100, which is why the 100 is on the bottom, and multiply by that to the other side, which is why it's up on top. So it's the exact same math if you just plug it in and rearrange as well. Any questions on mass to mass percent? So there are some other sort of percent concentrations that you sometimes come across in addition to sort of mass to mass percent. And let's just talk about some of those as well. So there's one that deals with volume, and there's one that sort of deals with mass and volume. There is, in addition to percent mass to mass, percent volume to volume, like an alcohol, and that is the volume of solute divided by the volume of solution times 100%. This is typically, in most cases, kind of like milliliters on top, milliliters on the bottom type of deal. This one, you don't have to worry about the bottom one, because usually in the volume, they just give you the volume of the solution. It's not separated or anything like that. And there's also percent mass to volume, which is the mass of the solute divided by the volume of solution times 100%. This is basically like grams over milliliters. That's like density, basically. Yeah, this is basically that deal without the multiplying by 100. Now, they all work the same. You could plug into this equation just like you could do with the mass percent. You could also, again, if you had the 5.2% by volume sodium chloride solution, that would mean you had 5.2 milliliters of sodium chloride and 100 milliliters of solution. And you could obviously flip it as well if you needed it. And again, if you had 5.2% mass to volume of sodium chloride, that would mean you would have 5.2 grams of sodium chloride over 100 milliliters of solution. So very much like the mass percent, is kind of very similar type calculations. You could kind of either plug it in, or if you're given the percentage, you could kind of turn them into usable conversion factors. So those are sort of the three sort of, if you will, I get percent concentrations. Mass percents used a lot, percent by volumes used a lot, like I said, with beverages and stuff like that is used, a lot in terms of that. Any question on those two there? Okay, so we talked about these sort of percent concentrations. Let's talk about really the major sort of unit of concentration that we see the most, and that is molarity. Probably the most common and the unit of concentration you see the most in chemistry is molarity. And molarity is abbreviated with a capital M, and it is moles of solute over liters of solution is the actual sort of definition of it. You could think of the molarity formula there as like a formula. You could oftentimes use it to solve for any of those three things, depending on what's given to you. So if we wanted liters would be moles divided by molarity, multiply liters to the other side, divide by molarity. And the one that is used a lot when you have sort of molarity and volume is to use it to find moles. Moles is liters times molarity. So those are sort of a couple rearrangements of the molarity sort of equation. And it's really important to know how to rearrange it and solve for any of those things. A lot of times things are not given to you perhaps in moles, but they're given to you in grams. So we could just do our basic kind of molar mass conversion from grams to moles. So that's a very common thing that you have to do, is go grams to moles using the molar mass from the periodic table to do that. The other common thing is a lot of times we deal in milliliters. So you have to do that milliliters to liters conversion a lot when you're using molarity. And it is 1,000 milliliters, right, is 1 liter. You definitely for sure, I will say that when you're doing this move here, or again, whenever you're using molarity, you should make sure you have it in liters, so everything will work out correctly for sure. So when we talk about a solution that is 1 molar, for example, and that is how you kind of word it. If you have 1 big M, it's basically 1 molar. What that means is, for example, if we have 1 molar sodium chloride, you can get rid of the big M and convert it into 1 mole per liter of sodium chloride. When you do that and get rid of the big M, the number always stays with the moles, and it's always 1 liter. I highly recommend that you do that when you do calculations, because people leave the big M and frankly, they have no clue where liters is, where the volume is. They forget about it and everything like that. it's probably really good practice. Get rid of the big M in calculations, convert it to moles per liter. That way you can see both units. You don't forget about both units. And it's a really good way to calculate it is kind of do more of a dimensional analysis type calculation where you can kind of see the units to make sure everything cancels out correctly. So what does that mean in terms of concentration of ions? Well, because if you had something like sodium chloride in a solution, it would break apart into basically a sodium ion and a chloride ion. If the whole entire thing was 1 molar, the concentration of the sodium ion, because it's a 1-to-1 relationship, would also be 1 molar. And if you're interested in just the chloride ion, it's a 1-to-1 relationship. It would also be 1 molar. So how you deal with concentration of just ions is you kind of do like a stoichiometry relationship. If it breaks apart into a 1-to-1 relationship, it's the same number, multiply by 1. Breaks apart into a 1-to-2 relationship, you need to take the molarity and times it by 2. So what do I mean by that? If I had a 1 molar calcium chloride solution, and I want to know what is the molarity of the calcium ion and what is the molarity of the chloride ions, I would take this, and when this goes into solution, it would break apart into a calcium plus 2 chloride ions, right, when it breaks apart. So if this was 1 molar, it is a 1-to-1 relationship between just the calcium and the whole thing, which means its concentration would be 1 molar. It is a 1-to-2 relationship here for the chloride ion, which means you would actually take the concentration and multiply it by 2. And the concentration of the chloride ions in that solution would be 2 molar. You get twice the amount of chloride per calcium, is twice as concentrated. So it's twice as concentrated in terms of the chloride concentration. And you may ask, how do you get there really? Besides the quick way like that, the long calculation to that is you take 1 mole per liter of calcium chloride. You do a stoichiometry mole to mole relationship, which is 1 mole to 2 moles. 1 mole of the whole thing gives me 2 moles of Cl minus. The moles of the whole thing cancel, gives me 2 moles of chloride per liter, which gives me 2 molar for the chloride. That's the long way of doing it. The very quick way of doing it is it breaks apart into 2, times it by 2. Breaks apart into 3, times the concentration by 3, and it'll always work out that way. Any questions on that there? That's basically, it's 1 liter of a solution is basically what the bottom means, yeah.
Okay.
So basically in 1 liter of that solution, there's 2 moles of chloride ions floating around. Yes. Uh-huh. So if you have magnesium and you put it into water, you could get that with some magnesium hydroxide being formed.
So the thing is the volume of that gas be added to the volume of water?
It wouldn't be. So the volume would still be probably whatever the volume of the container is in. In that case, it would still be the same sort of liquid volume, if you will, for the molarity part, if that's sort of what you're asking. Yeah. And remember, when we talk about volume of gases, it's really related to the container it's in anyways, right? We don't really look at the sort of volume of the gas itself in an ideal situation. What's that?
I think I'll wait till you get there.
Okay.
You keep going ahead to the next example.
Okay. All right. So that was just a little side trip there of some applications of molarity. What's actually calculated here. So take a couple minutes here and calculate the molarity of a solution that's prepared by dissolving 15.6 grams of KBr in enough water to make 1.25 liters. Let me give you some periodic table stuff that will be helpful here. That is 3910 for potassium, and bromine is 79.90. Okay, let's take a look at this since we're getting to the end here. So we do want to calculate the molarity. And again, remember, molarity is moles per liter. So what we want to first determine is, do we have any of that? And we do have the liters of solution, and it's actually in liters, so you don't have to do any conversion. Again, if it was in milliliters or some other unit, you got to convert it to liters there. So we really do have the bottom. So really the thing that we are missing to calculate the molarity is the moles. And we don't have the moles of the solute, which is the KBr in this case, but we do have the grams of it. So we can use the molar mass here, right, to convert those grams into moles. So in this case, it's one of each, which should give you 119 grams per mole when you add those two together, basically the KBr. So to convert to our moles of KBr, it would be our 15.6 grams divided by our 119 grams per mole. Grams will cancel, and that will get us 15.6 divided by 119, 0.131 looks like moles of KBr. That is the top part of what we need. Now that we have both, we could actually just put it into that formula. The molarity would be our 0.131 moles divided by our 1.25 liters. And if we do that, we will end up with 0.105. 105, there you go. 05. Now, in terms of units here, they do not cancel. So they still are there. So you could write it one of two ways. You could write moles that goes with the number over liters, or you could write 0.105 big M and maybe like a KBr there to make it all nice. Any question on that calculation? So it's a very common thing, grams to moles, moles to grams, using molarity. And you want to make sure liters definitely when you're doing molarity. Any questions on any of that there? Okay, so I think today's lab is like all about this stuff.